Okay, so we've done a good start about from looking at potential in a capacitor, seeing how that relates to energy. Let me go back to my PowerPoint because there's just to highlight the connection between potential and energy. All right, we looked at this. So here's kind of another picture. That might be helpful. So if you're taking this charge here, this charge right here, okay, we're taking this charge here and we're going to move it over to these charges. Okay, now these charges are, we're going to see later, are creating a potential, right? So it's going to require some energy to get these over here. So I'm going to use, according to this picture, 4 microjoules to push this charge here. Whereas if I go along this path to this distance, right, it's a lot closer to these charges, so the repulsion is going to be greater. It's going to take more energy to do that. Okay, so the potential energy, that's a higher potential energy. Where do these 4 microjoules of work go? Like once I applied the force, where did that energy go? Well, it went to potential energy. So this charge now has more potential energy, right? Because I pushed it. If I push this charge along this path, it has even more potential energy because it's, again, it's closer, more repulsion, so more energy being stored. Now, all these, remember what I said about energy, all this energy comes from interaction. This charge is interacting with these 4 charges. Same thing here. This charge has a stronger interaction with these 4 charges, right? Because it has more energy. All right, now let me take out that charge. I'm gonna, sorry. Okay. I'm going to take out this positive charge here and just have points in space. So that's how it looks like. Those points in space now have are voltages created by these charges. And these voltages, remember, it's not energy. We don't have interaction between 2 charges. What I have written up here, the electric potential is created by the source charges. So voltage is created by these charges. And it exists at every point in space. So A, B, and C, and everywhere in between. So you have voltages everywhere in this space here. And what again, the voltage, the whole point of a voltage, this 400 volts and the 600 volts, is to tell you how much energy is it going to take if you're to put a charge there, right? So going from 0 to 400, that's a greater increase in voltage. So it gives you an idea of how much energy is going to take to move a charge once you actually put a charge there. It's going to tell you give you an idea of how much energy is required. Same thing here, from 0 to 600. Well, you see 600 volts. You know that if you actually put a charge there, it's going to take more energy. Okay. So just a different picture of what we talked about already, so that I don't know, some things click better than others. So I'm hoping that helps you see that potential and potential energy. We're talking about 2 different things there. They're related, definitely, but they're 2 different things. Okay, I'm going to ask you guys this question. So I have this source charge. This source charge is, like what I said, creates the potential. And I'm going to move 2 charges here. One situation, I'm moving the positive over here to some distance r between these charges. Another situation, I'm moving a negative charge here. Okay, which situation here do you have greater electric potential? Is it greater in situation 1? Is the electric potential greater in situation 2? Or are they the same for both? All right, so let's look at this. If we're talking about the potential, right? Remember potential here. Potential is not an interaction, right? It's just created by the source charge. So this positive Q and this negative Q here, these 2 do not affect the potential. The only thing that affects the potential is this guy right here, the source charge. So we have the same source charge for both scenarios, right? And same distance, R and R. it should be that the voltage should not change because it's independent of whether you put a positive Q there or whether you put a negative Q there. All it depends on, the only thing potential depends on is this source charge here. So same source charge in both scenarios, so you get the same voltage for both scenarios. Okay. All right, now let me ask you this follow-up question here. Now, look at the question, it's different. What is the electric potential energy? So now I want you to focus on the energy, right? Now we're actually looking at the interaction. So which one has a greater potential energy? Okay, so we are looking at the interaction. We want to know potential energy is interaction. Which interaction is greater? Let me talk about C first. So I could see why you would say the same for both. Both charges are the same distance from the source charge. What we're talking about, they have equal charges, just opposite sign. So remember our equation for this. Our equation for I got my pen here. Okay, our equation for potential energy that we saw last class. KQ over R. Okay, that was our equation. So I can understand why you would pick both, right? Same values for Q, same distance for R. So you should get the same. But with potential energy, signs do matter. You could have a negative potential energy. And situation one, well, Q and Q are positive. That is going to be a positive potential energy. So I'm just going to put here plus U. Okay, whatever U is, once you plug into your calculator, you get a number. Okay, so you get a positive potential energy there, but for situation two, you get the same value for U, but it is a negative, so you're going to have a negative potential energy here. Okay, you guys dealt with negative potential energies before. I think I might have talked about this last class, where negative potential energy you saw between two planets. Okay, so kind of the same idea here. Anytime you have an attractive force, that's going to give you a negative potential energy. All right, so hopefully that kind of helps you answer the question there. So situation one, you have positive potential energy. So situation two, you have the same value, but it's negative. So the question is, which one's greater? Well, it'll be situation one. All right, so I just want to run through those examples before we actually got to potential. So let's get to potential between 2 point charges. Okay, so potential between 2 point charges. Or not between, but potential from a point charge. So that's what we're going to look at. So potential from a point charge is closely related to energy. So if I take, let's say I take one port positive here. Positive charge here, positive charge here. Okay, there's more energy in this case than, let's say, this one. Okay, so in my first situation, R1, well, R1 is a lot smaller than R2, and we were already seeing earlier that potential energy is dependent upon distance, right? So the further out these two charges go, the less energy we have. Okay, that's what we have there. Let's say what would happen if we put let's take out these charges. So I should probably notate which one's my source charge here before I go any further. So let's say this is my source charge. I'm calling it capital Q. Okay, that's my source charge. What I mean by my source charge, that's the charge that's creating that potential. All right, so let's take out the other charges here. So erase these ones here. And I'm just gonna put points, empty points in space here. So here's these empty points in space. What's going to be the potential? How do those potential compare? How does the potential in R1 compare to the potential in R2? Well, R1 gave me more energy. So more energy means that there, at that point, you're going to have a higher potential here. Higher potential, higher voltage, right? That's what potential is. Here, R2, you get further away, and we said when you go further away, you have a lower energy, right? If I had that other charge there. When I don't have that charge there, I have a lower potential. Okay, and we can easily calculate that. We know V equals U over Q, where this Q is not the source charge here. This Q is the, I don't know, what's the opposite of a source charge? I don't know, I'm just gonna put not the source charge. It is not this it is not the charge creating the voltage. Okay, not the source charge. So, so U would be K. I'm going back to our equation we just had. The source charge times the non-source charge, the one that's experiencing the energy, over R. That's my equation for U. Divided by Q, and I get my equation for voltage, K Q over R. Okay, that's my equation there. Quick note here. Do not plug in absolute values for your charges. Okay, in other words, if it's a negative charge, plug in a negative number. If it's a positive charge, plug in a positive number. And that's important because you can get negative voltages. Okay, a negative voltage, it comes from a negative charge. Okay, and a positive voltage you get from a positive charge. Okay, so we definitely do want to plug in the signs. Okay, so if it's a negative charge, plug in a negative value for your Q. Okay, so I'm going to represent this in a different way here. Let me go. Here's my source charge. Let me draw my source charge. And what's going to happen to that source charge is that the voltage drops as you go away from it. So I'm going to draw these lines here. Yeah, I'll answer their question soon, Adam, about the group work. Let me draw these lines here. Okay, so let's say all around this line, it's the same voltage as I go, right? I'm at a constant radius from the charge, a certain distance away from the charge. So let's just say that's, I don't know, 10 volts. And then another line over here. Try my best. Okay, another circle, supposed to be a circle, around this charge, it will be something like 5 volts. Okay, so these are called equal potential lines, or surfaces, more accurate. Let's see. Okay, so these are the equal potential surfaces. Equal potential surfaces are surfaces, three-dimensional surfaces where the voltage is staying constant, right? That's an equal potential. Okay, so there's this sphere. You want to imagine this in 3D. They have a positive charge in the center. There is this sphere where the charge is in the center of that sphere. A sphere of just 10 volts around the charge. You go a little bit further, right? You have a larger charge. Sorry, a larger radius, a larger sphere, and on that sphere the voltage is 5 volts. I go a little bit further, and I'm not going to draw it, but if I had a bigger sphere here, that voltage might drop down to 3 or something. Okay, so these are the equal potential surfaces. We actually saw this already earlier, let me go back a few slides, right here. These are also equipotential surfaces, right? All along these lines here is you have a constant voltage. Like, so this will be your 10 volt equipotential surface. This will be your 15 volt equipotential surface, you know, et cetera. Okay. All right. Let me go here. So I have a kind of a better picture, I think. Let me go to it. Okay. So here's the equipotential surfaces. You can see what happens to potential as you go away from the voltage. Oh, sorry, as you go away from the charge. Oops. Okay, as you go away from the charge, so the charge will be at the origin. As you go away from the charge, voltage drops here. Drops according to, you know, that's your 1/r function. And then here's kind of a 3D picture. You have the charge in the center. You have a sphere, right, that has a certain voltage, V1, or 3V1, I guess. The sphere bigger than that one is going to have a lower voltage. So everywhere on that sphere is some constant voltage. And you have another sphere, right, around that, which is a bigger radius. And at that bigger radius, you're going to have a smaller voltage. Here's how it will kind of look like in a two-dimensional depiction of it. Okay, you just have these circles. Again, these circles represent surfaces where voltage is staying the same. Okay, your voltage is keeping the same. All right. Okay, so let's do an example with voltage. Yeah, I'll do my own example. Kind of picking and choosing from my PowerPoints, but I think I told you guys before that those PowerPoints are for another class. You guys, that's for my 2B class. I use PowerPoints there, but for you guys, I'd rather not use PowerPoints. Okay, so let's do an example here. Okay, so I'm going to have two charges. This is going to be a 10 nanocoulombs. And that'll be a negative 10 nanocoulombs. Okay, and what I want to do is find the charge, not the charge, the voltage. What is the voltage midpoint? And we get that different color. I think that's about midpoint. Okay, what's the voltage at the midpoint between these two charges? I'll call this point A. And what is a charge when you're a little off center, like 3/4 of the way to 10 nanocoulombs? Let me call that point B. I'll give you some numbers here in a second. Okay, so A is halfway, B is 3/4 of the way to the negative 10, and the distance between them, 10 centimeters. Okay, so let me write out the question here so you guys could follow along. So 2-point charges separated. Centimeters. What is the potential? Midpoint, A. And B, 3/4 of the way to the negative charge. Okay, so that is our what we're doing. Okay, so One thing you have to keep in mind about potential. So potential is a scalar. It's not like a vector with electric fields, or like electric fields. If potential is a scalar, that means you don't have to worry about direction at all. So for part A here, part A is actually pretty easy. If we want to find voltage, total voltage is just the voltage from the positive charge plus a little bit better. Plus the voltage from the negative charge. Okay, all we have to do is add up those voltages. And there's no cosines there. We don't have to worry about whether the voltage is pointing to the left or to the right because voltage is not a vector. Okay, it's just a number, it's a scalar. Okay, so I just got to plug in my equation for point charges. It's going to be K positive Q over R, where R is the distance to the point A. So I'm talking about this R right here. That's my R. So it's to the midpoint. Plus KQ minus over the same R, right? Because we're talking about the midpoint. What should that equal? Let's take a guess. Yeah, it's going to be 0. Okay, so you got Q is your positive charge, which is a positive 10. The negative Q, well, it's a negative 10. So you have positive 10 on one side, negative 10 on the other. R, because we're looking at the midpoint, right, for part A, the R values are the same. So this term here gives you a positive number, whatever number that is. This term here gives you exact same number, but negative. So you add them together, and what that tells you is you get 0 volts at that midpoint. Okay, so part B is a little, we do have to plug in numbers there. So for part B, what is the potential 3/4 of the way to the negative charge? So in that case, I gotta be careful about my R's. It's gonna be, I'll call this my R positive, R negative. Okay, so the R's aren't the same in this example for part B, because again, we're not looking at the midpoint. All right, so finding my total voltage, same equation really. We're just adding up the voltages, V1 or V positive, plus the voltage from the negative charge, V negative. I'm just gonna plug that in there. K, let's see, K Q positive over R positive plus K Q negative over R negative. All right, so I'm just using my equation for my voltage there. And I just got to plug in. So remember, I'm going to factor out my K. K is your 8.99 times 10 to the 9. And then I have Q positive, which is 10 nanocoulombs, over the distance. Now that distance, we're talking about 3/4 of the way. Okay. So that's not, doesn't turn out to be, what's that, 30 divided by 4? I don't know. What is that? 7 points. I don't know. I don't have my calculator. It's much easier in lecture because I just ask you guys to do it. So the distance 30 divided by 4. All right, so yeah, okay, so 7.5 there. 7.5 for the positive, and then plus the negative. So I am going to put the negative there. Plug in the negative. Okay, and then that will be 2.5. Okay. So yeah, thanks. I didn't see that in time. Okay, so There we go. We plug in our values. This, in this case, does not equal 0. Let me see if I could write that a little neater. Oh, so let me rewrite that. It should be in, so 7.5 times 10 to the negative 2. I guess it would be just easier to write decimals. And then over here, so 0.025, yeah. Okay. So we should get a negative 2400 volts, which makes sense. If you think about what we got our 0, right? Our 0 was midpoint, right? This is 0 volts. If you go towards a positive, our total potential should become more positive. So all this is positive voltage here. If this is 0 volts and you go towards a negative, your voltage becomes more negative. So we do expect a negative answer here. Yeah, okay, that looks right. So negative 2400 volts. All right, so that's how you calculate voltage. Again, the whole, I think you should be ready for, or to be able to answer is, once you get this voltage, and I say, what if I placed another charge there? How much energy would you get? And that's where this equation comes in, right? So that voltage there just gives us energy. That's kind of its point. Once we calculate voltage, all we got to do is multiply by the charge that's being placed at that point. Okay, so the charge that's being placed at point B, let's say, we plug it in there, and that gives us how much energy that has. Okay, when we come back, I'm going to spend the next 20 minutes talking about the relationship between electric field and potential. So, which is what your lab's about. So we'll do that after our break.